go straight to that first slide. So I'm going to connect measurements in classical and quantum theory, and in particular to the normal distribution of position measurement of a classical particle, and the order will get related. And in fact, both will be derived from the same setup, and the setup is based on the Schrödinger equation. And I know it sounds very contradictory, and particularly two cat killers, but I will explain this in a minute what that means. And the starting point will be, a simple connection, but very interesting, well-known connection between classical and quantum dynamics. So if you consider, in the case of a single particle, so if you consider a subset in the Hilbert space of states of a particle formed by wave packets, Gaussian wave packets with a small variance, sigma squared, and so then we consider the action function for the Schrödinger equation, but constrain the states phi to belong to this subset M. So then if sigma is sufficiently small, you can show that this action functional gives you this subset, the action functional for a classical particle. Okay, so then the idea is, maybe I could explain a little. So the idea is that maybe classical physics and the classical world is just a submanifold in the Hilbert space, or maybe Hilbert manifold more generally. And so I'm going to argue in favor of this idea. So first of all, of course, if M has something to do with the classical space or classical phase space, we have to introduce some structure on it. And it's easy to do because, of course, on L2 we have a Hilbert metric, and so we have a Riemannian metric, in particular in the sphere of normalized states. And then we can introduce the Fubini's 2D metric on the projective space of states. And of course, there is a simple relationship between inner products of vectors orthogonal to fibers of this projective space vibration. And the Fubini's 2D product of the corresponding images. So we actually get, therefore, a induced Riemannian structure on this set. So the set becomes a manifold, and in fact, a Riemannian manifold. Okay, if we consider then this M sigma 3 manifold now, and actually a submanifold of it formed by Gaussian states or Gaussian packets with p equals 0. So then we obtain a simple map. So here it is. That basically maps parameters A and P into states. And so because there is metric everywhere, you can ask what kind of map is it. It turns out that this map is an isometry of, in the case P equals 0, it's isometry of R3, into this M3 manifold, and in the case of classical phase space, you start with R3 plus R3, and once again you get Euclidean structure. Now, the reason I show this in some kind of wiggly way is that both of these manifolds are complete in the Hilbert space. So there's no vector in the Hilbert space that would be orthogonal to all of the manifold M. So it goes through dimensions of the Hilbert space, and that's why I show it in this wiggly way. Okay, so now if we think that M has something to do with a classical phase space, or classical space in the case of M sigma 3, then we better explain how the Schrödinger equation is related to Newtonian mechanics. And of course, the first step would be to actually separate component of the velocity. Obviously here we have a velocity of state on the left side of the equation, and you can think of the right side as a vector field. on the sphere of states or on the projective space. And so we are talking now about decomposing this velocity of state into components, first of all, parallel to the fiber of the vibration and orthogonal to it. Now, parallel, of course, gives you the expected energy. The orthogonal component right here, its norm is equal to the uncertainty in energy. And so you obtain a very simple, well-known result, in particular that the speed of evolution of state in the projective space is equal to the uncertainty of energy. Now, we could do more, though. So with this component here, that is the orthogonal component, we can decompose it further, again, for states in this submanifold. So in fact, here's the component that is the expected energy, and the remaining thing are related to the uncertainty. So they come from, you can see the velocity term, the acceleration term, which are, of course, classical phase space components of a motion of classical particle. And then the last term is velocity of spreading of state. Again, it's assumed here that the state belongs to the submanifold, obviously. And you can also relate commutators for the states in M with plus ohm brackets. And so, to put it shortly, Newtonian dynamics in this way is the Schrödinger dynamics constrained to a submanifold. All right, so there's Newtonian dynamics. Now, talking a little more about the metric structure, well, there's this simple relationship between the Euclidean metric, A minus B squared. For the states, of course, I'm still considering states in the submanifolds. And theta is the Fubini-Study distance between the states. And so it turns out that there's this simple relationship. And so on the right side, once again, we have a Fubini-Study distance. And of course, this is just the probability of transition from this state to this state. And something similar can be obtained for the classical phase space submanifold. Now, this is interesting because it relates now the probability of transition to something that looks like normal distribution. So the probability to find particle at the point P if the initial position of the particle was A. And in fact, this relationship immediately extends in the sense that if you assume, this relationship is true just because of the isometry, but if the Born rule, which is the right-hand side, is true on the submanifold, then it's easy to show that it must be true on the entire Hilbert space, provided the probability of transition depends only on the distance. Okay, so is there any way to use it to relate measurements in both theories? Again, so if you measure position of a macroscopic particle, we get generically normal distribution of the position around the variable, but because of this embedding into the space of states, and because normal implies Born and the other way around, then we can indeed move on to relating the measurements. Now, what does it really mean? First of all, normal distribution could be derived from Brownian motion. So you can think of, measured particle as experiencing random kicks during the process of measurement because of the influence of the environment. And so, we get this Gaussian spread as a result. But Brownian motion technically could be derived from Newtonian dynamics. And now it was just shown that Newtonian dynamics is a constrained Schrödinger dynamics. So the question is, what kind of Hamiltonian would give us this Brownian motion on the submanifold? And there is a hint from this BGS conjecture. The Brownian motion can be modeled by a chaotic process. We can consider, for example, motion of particle in the lattice of round obstacles. But for if the classical process is chaotic, then the BGS conjecture says that the Hamiltonian of the corresponding quantum counterpart must be represented by a random matrix. And so therefore, I put forward the conjecture that the state of microscopic particle whose position is measured actually satisfies the Schrödinger equation with a random matrix from the Gaussian unitary ensemble. And then the matrices representing the Hamiltonian at different times are independent and belong to the same ensemble. Now, is it really realistic to make this assumption? I mean, one thing that immediately follows is that if you condition the random walk that satisfies the conjecture to stay in the submanifold, then the submanifold M here, then what you get is a random walk on R3, the usual Euclidean space that models Brownian motion of a particle. So it's an interesting result, not too complicated to prove. And then, of course, the Born rule, because remember, normal implies Born provided the probability of transition depends only on the distance between states, which is the case in the case when the Hamiltonian is a random matrix in GUE. And by the way, I should also mention one thing, that the Brownian motion on the submanifold here can only be obtained if H is in the Gaussian unitary ensemble. It wouldn't work for the orthogonal ensemble. And the Gaussian unitary ensemble, I mean the Hamiltonians in the GUE correspond to systems that are not time reversible. And so it's interesting that this ensemble is needed to actually obtain the Brownian motion from the random walk in the conjecture. Okay, so we get the normal distribution, we get the Born rule. So what is going on with the state according to this picture? So here's the projective space of states, or just think the sphere of uniformized states. You start with a certain initial state, and then it just randomly spreads over the sphere and has a possibility of reaching the submanifold. If it does, then the probability of reaching a particular point in this submanifold versus another point will be given by the Born rule. Alright, so is there any way to use it to address some issues in quantum mechanics? So in particular, let's assume that this conjecture is valid about the random matrix representation of the Hamiltonian. Then it's possible to show that the state of the particle is constrained to the submanifold M precisely when the induced Brownian motion of the particle vanishes. I mean, again, remember, we have, maybe I should go back for a second. M is a submanifold in the Hilbert space of states. If the state spreads isotropically, then of course, if you know that it doesn't spread along the submanifold M, then it doesn't spread at all. And of course, we know that for macroscopic particles, that's the case. They don't experience Brownian motion. If you have a ship in still water, it's not going to move because of the kicks from molecules of the water. So you obtain, therefore, the result that, close to time? Okay. 10 minutes, right? 10 minutes. Okay. Right. So you obtain, therefore, the result that, it becomes possible to explain why macroscopic particles are not present in several places at once. Let me explain a little bit more to this. So if you consider, the spread of state actually is related to the distance from the state to the submanifold. In particular, if you consider a Gaussian state with a spread parameter d different than sigma, or maybe equal to it, then you obviously obtain a simple relationship for that describes the Fubini-Study distance between states. Now, of course, if d is equal to sigma, you get the distance equals 0. And if d is much larger than sigma, so the state is spread, then the distance becomes close to pi over 2, which is the largest value. So, on the projective space. So, in other words, we see the electron or other microscopic particle as a particle when its state is close to the submanifold, and otherwise we see it as a wave when the state is away from the submanifold, that is further in the space. And in this slide, we could also look at double slit experiment. What exactly happens there? Well, the conventional picture is that even if you have a Gaussian state to begin with, it goes to the slits, and so there is this, after the slits, you get a superposition of two Gaussians. But what does it mean, superposition, right? So a single Gaussian is a point in the submanifold M, but superposition is a point which is away from M. And so really what we see here is that the path of state just picks up. It goes away from the submanifold into the space of states. And of course, a good question, what happens after that? But because I run out of time, I'll leave this question. So the summary, though, is that it may be that macroscopic and microscopic particles are not so different. And the important difference is that classic microscopic particles just live on the submanifold, and they're forced to stay there. Remember the theorem regarding that. And then microscopic particles are free to leave the submanifold and go into the space of states. So some of the publications related to this are here. Some are currently in the journal, but I will be happy to provide additional information. Thank you.
Okay, so two questions maximum. Okay, so.
Thank you. I have a question. How crucial is it that you start with this ensemble of Gaussian states? Because the Gaussian state, I could think of a particle in harmonic oscillator potential, and a particle in harmonic oscillator potential with such a wave function, describing it by a Wigner function, is completely classical in the sense that the Liouville equation and von Neumann equation in this case are identical. So in some sense, this restriction to Gaussian states is already putting the whole thing very close to classical.
Yes, of course, it's very close, and that's not surprising. Coherent states are the states that describe this transition from quantum to classical. So this part is not at all new. What I was trying to do is to extract a connection between what happens, with microscopic particles, with what happens to macroscopic particles, rather than just concentrate on transition to classicality, which, of course, clearly, as you described, is just innate already to begin with.
Hi, just a quick question. So, if I understand correctly, this dynamics is on a particular manifold which has all possible states, and then collapse would mean that you're restricted to a particular submanifold which are just classical states.
Collapse is going to be, geometrically speaking, this transition from a state that is not on the submanifold to a state that is on the submanifold.
Yes, indeed. So then I would like to ask, if you do an experiment, something like an experiment with a spin, for example, and after a projective measurement you get a state 0 or 1 or something. In a different basis, this would be a superposition state, but just looking at it, it seems to be some sort of a classical state, the expectation values of which will probably follow some sort of classical equations if the Hamiltonian does not commutes with rest and so on and so forth.
Right. Okay. Well, I mean, first of all, the picture that I described does not include spin, right? So we're really talking about scalar particles here, no spin. Although, of course, the good question would be how to include spin. But second, even talking about continuous spectrum and the position momentum operators. Yes, I think what you mean is that, yes, the state could reach the submanifold M, but it could also reach a different submanifold, that, for example, would represent particles having a definite momentum. I mean, to use an analogy with the speed, right? Yes, of course. But that's the beauty of it in a way, right? Because you still get the Born on that submanifold as well. So that is, if you Sorry about that. So, so if you ask a question, what is the probability of getting a certain position versus a different position, you get the Born rule for position variable. But if you ask, what is the probability of reaching a certain momentum versus a different momentum, then you get a Born rule for the momentum. All of these manifolds are submanifolds in the space of states. And again, because of the isotropy, there is the state could move one way or another. And so you get needed probability.
Okay, thanks.
Okay, so for the sake of lunchtime, we have to move on, so it's time to speak again.